Gopi? Where?
Yes, sir.
Shall we start?
Yes, sir. We shall start the session, sir.
Hmm?
Yes. Good morning, sir.
Good morning, sir. Ranjan, sir.
Good morning.
Good afternoon, sir.
Good afternoon.
Thank you very much for accepting our request and
Already this
giving
is
this
hard actually.
presentation.
Huh?
Giving this presentation in AICTE sponsored STTP on converter technology used in renewable energy sources like wind and solar systems. Thank you very much, sir, for accepting our request.
Thank you.
Now, I request Mr. Gopinath to introduce our today's speaker, Dr. M. Ranjan Kumar Behera.
Yes, good afternoon to one and all. Honorable Secretary, sir, Principal Madam, Convener, Co-Convener, most value invited guest, fellow faculty members, and participants. It's my immense pleasure to introduce today's speaker, Dr. Ranjan Kumar Behera, sir. Dr. Ranjan Kumar Behera, sir, completed his engineering degree in electrical engineering from Regional Engineering College, which is presently NIT Rourkela, in the year 1998. Then, sir completed his MTech and PhD degree in IIT Kanpur in the years 2003 and 2009, respectively. He worked as trainee engineer in Hindustan Aeronautical Limited, Sunabeda, in the year 2009. He presently, Ranjan Kumar Behera sir, is a faculty member in the Department of Electrical Engineering, IIT Patna. Ranjan Kumar Behera sir has been worked as head of the department between the years 2016 to 2019 in IIT Patna. Ranjan Kumar Behera sir has been a visiting scholar in the Energy System Research Center, Tennessee, University of USA, and as a visiting research collaborator at a EC department, University of Pretoria, South Africa in the year 2016. He got several international and national awards such as Young Scientist Award in the Engineering Science from DST, Government of India in the year 2001, selected as a faculty featured engineer of a global 2015 USA advance for the work he has done in advanced solar research in the Institute of Tencent Technology University, USA. He published more than 100 journals in a renowned national and international conference papers and proceedings. His currently research areas interested are power electronics, high power motor drives, smart grids, IoT applications. Presently, Sir is a co-author of a book entitled Power Electronics Drives and Advanced Power Applications, CRC Plus. Thank you, sir. Thank you, Ranjan Kumar Behera, sir, for inviting our request.
Thank you, sir. Actually, I'm really greatly honored by your institute, especially your HOD. Yes, sir, and thank you all. And thank you, sir, for nice introducing. And I had a good student. He was doing BTech here, Gopinath. So your name remember. So, uh, so can you hear me, sir?
Yes, sir. There is a little disturbance, sir, but your voice is a little low, sir.
No, okay, okay. No, no, actually, I'll start from my mobile. Maybe it will be little good because sometime. So let me stop this video. Now you can hear me.
Yes, sir.
Huh?
Yes,
Or
sir.
I'll start from my mobile and maybe presentation from the desktop. That will be good actually. So
Okay, sir.
there's some problem in this mic, And I tried to rectify new mic also, but still this is has some problem. So let me join from my join the meeting. Hear me, sir? Sir, is it better?
Yes, sir. Yes, sir. Now it is loud and clear, sir.
Okay, okay, this is for my mobile. Okay, thank you, sir. So, okay, I'll switch on the video or switch off.
You can do it either, sir, as you wish, sir.
Okay. So today, just I'm sharing my screen. Hope it is visible to everyone. Okay, good afternoon, and thank you, Gopinath sir, for introducing very nicely. Although I am not such qualified, just I am also a student, and I learn from my students, and that one only I teach to everyone. So thank you very much, sir. And I'm very thankful to Dr. Bhimaya sir and your HOD also, and to your institute. So this is my third lecture. So first lecture we discussed about the advanced controller, special current source inverter control, and a few harmonic contents we discussed. And the second FDP program, we discussed about dual active bridge converter and all solar microgrid system. And we discussed also few projects which we implemented here at IIT Patna. And today we will discuss the nonlinear control, especially the hysteresis current control, which is a very, very popular, and it is a very great application in all kinds of, starting from industrial drive to grid integrated inverters. So today we will go through some of the basic fundamental up to the nonlinear technique, and then we will discuss the global optimization technique under the partial shading condition, if time permits. Okay, so I'll go through this one, and anybody has any question, you can put in the chat box, and after each section we complete, I will open for the discussion, and hope all of you will, if you have any questions or comment, we will try to answer those questions, and again we will continue with our discussion. Okay, so till whatever time we can. So I think this is 2 o'clock. Up to 2:30, I'll try to present, and half an hour I will keep for discussion also. Okay. So today is I will discuss advanced current controller for power converter in solar grid interface. Okay. So if you see the generic control structure for a photovoltaic system, and is like this actually: PV panel connected to some kind of DC-DC converter, then DC-AC, then some kind of a filter circuit, and through the interfacing or isolation transformer, connect to the grid. This is the basic system. The converter may be different kind of inverters, or DC-DC boost also different kind. It may be isolated, non-isolated. There are many things out there. And maybe it is grid connected, or it may be isolated system also. And we have the DC link control, synchronization, grid synchronization, and current control. And today, we will discuss more about current control technique with large solar grid interface. Okay, and other technique like MPPT, active filtering, islanding. These are the different control structure where different control techniques where we can see later into that. So if you see here, the power engineer, we don't study the physics of this. So physics is well known to the like multi-junction solar system and the polycrystalline, other kind of this power, this organic solar, all these things they studied by the microelectronics as well as the physics. So our thing is to generate this PV panel and then convert it and utilize it. And if there are some few techniques where we can do the fault tolerant analysis, reliability study, all those things comes in the subway. Actually, it is not mainstream. Our mainstream is to control the converter and extract maximum power from the grid or the solar and feed to the system or to the load. That is the main function of a power engineer. Now, we have a different kind of inverter structure, and most of the time, without knowing the inverter structures, we generally connect the different VSI converter and directly we want to control it. But if you see, there are a few inverter topologies which gives more freedom for the user and designer, especially to the researcher and the industries to go for minimum number of components so that the production cost can be reduced and the cost of the solar PV will be reduced. That is the main purpose. And third thing is to improve the efficiency. And fourth thing, that in solar, that if there is a transformer, you see the transformer actually became bulky. That is why we want to use the transformerless operation. So this is our PV array. You can see a filter and then a boost with a high frequency transformer. Last time when we discussed about active dual bridge converter, in that we have already studied the active dual bridge converter. There are few things which the dual active bridge converter, the size of 1 kVA transformer, it is simple, only 5 centimeter to 5 centimeter. Whereas actual 1 kVA transformer is very large. So high frequency you go means your component size reduces drastically. And your switching frequency increases, but switching ripple reduces. So that is why these high frequency transformers are very, very useful, especially in our grid interfacing transformers, okay, or the transformerless operation of the grid connected system. So this is a very high efficient, and then there are also boosting inverter, okay. So this inverter is connected, you can see just a DC-DC converter, then an inverter connecting to the grid actually, and LCL filter you can connect like this. So what is the grid requirement of PV? First thing is, the grid requirement is that the voltage harmonic level, that should be maximum THD is 8%. Total harmonic distortion is 8%. And voltage unbalance for three-phase inverter, maximum unbalance is 3%. So more than that, what it will happen, it completely draw different large current from the inverter. So that's what the overcurrent, it may exceed the overcurrent rating of the inverter. So it should be within 3%. And voltage amplitude variation, that must be the minimum or less than maximum is your 10%. Okay, that means less than that much variation you can possible. Okay? That is why it is possible, because you see, in case of a power system, I told you, I think, I don't know whether I have discussed it or not. In the power system generally, we have large network. In that network, sometimes what we do, we generally when there is a peak load, suddenly this grid connected system, they draw large amount of the power so that the voltage drops down. As the voltage drops, then you can understand that our flywheel start developing that AGC control is actuated, and you start catering the peak power demand of the of the load. So that is why there it is. You can see that there is supporting system, inertial supporting system, whereas in solar system we do not have like that. Okay, that is why the variation should be maximum 10%. And sometimes we use also the storage element like our battery system, which can provide as the this support in the voltage variation. Second one is the frequency variation should be maximum 1%. Okay, and voltage dip duration is less than 1 second, and they should be less than 60% of the voltage. That means the low voltage ride through is one of the important factors. See, low voltage ride through is a very, very important aspect actually. This low voltage ride through, they generally, it comes to the voltage when there is a fault or some kind of short circuit or abnormal operation. Okay. Now, there are different kind of power plant, the solar plant, that is small PV plant, and there are medium range or rooftop power plant. Okay, then you have a large rooftop power plant, then mini central inverter, which is greater than 6 kilowatt, and it should be less than 100 kilowatt. Then central inverter side, okay, so that is possible. So when we design the inverter for a PV system, so what are the difficulties? First thing is that the solar PV inverters are very complex, functionally also, because they require many things. For example, boosting the input voltage, grid connected filter, grid disconnection relay, and DC switches are the most important thing. Then MPPT or maximum power point tracking, anti-islanding and synchronization, and data logger are the typical requirement of PV inverter. So there are basic few inverters. You know, this is a simple full bridge inverter. Okay, so which is can be connected to the grid, but this should be very low power. Okay, so there are different switching techniques which these inverters are operated. They are unipolar, bipolar, and hybrid modulation. Hybrid means both the unipolar and bipolar added together became a hybrid. So like this, you know how we all know the operation of these inverters, and the why I am very important is that you see a solar panel, there is a stray capacitance between the panel and the ground, which is the most important part of this whole complete diagram. Because we know this inverter operation, all of you know there, you know very nicely. But there is a VPE, which is connecting from this panel to this ground. This is called the common mode voltage. So as soon as if your grounding is not properly planned, as soon as you touch here, you will get a short circuit like a thing, the current will flow. So that is why then solar panel we always design the separate grounding system of that building. If there is a grounding system in a building and you want to put a solar plant, but that grounding cannot be used for this. Okay. So there are bipolar modulation, unipolar modulation. I think all of you know this bipolar and unipolar. The most important thing that unipolar modulation, you need to get a zero state. Okay, how you will get it? Just by circulating, okay, the current within the multiple switches and the source. And then we have a unipolar switches that you can design. And then there is a this unipolar switches. There is different switching state, and this leg A and leg B are switched. The most important thing that the high leakage current and electromagnetic interference will occur in this. That is why we use the hybrid modulation, means partially the unipolar and partially bipolar. Then there are a few inverter structures, especially this H5 inverter. It was invented by one Switzerland company, like Solar Ping. So they have invented this switch. You can see here. There is an inductor in the source side, and there is a capacitor in the PV side. So if you directly connect without this S5 inverter or S5 switch, so what will happen? This diodes will be forward biased. Okay, any one of the diode will forward bias. Always it will be forward. So what will happen? This CPV and L1, they both will interact, and that is called the reactive power exchange between CPV and L1 and L2. So what will happen? This is reactive power. What do you mean by reactive power? I think I told you, when you have a small kit, we carry that kit to different places. How we carry? We take a big cotton, and this big cotton, in that cotton we carry the baby. But the cottons are not important. The baby is the important. So the baby is our active power, and the cotton which covers the baby, that is a reactive power, which is nothing but a carrier. So this carrier, when these are oscillating more and more, it affects and the performance of your inverter. And that is why you can see here, there is a diode D5 and S5, which is connected and disconnected, so that this reactive power exchange between CPV and L1 and L2 are properly controlled due to this switch. That is what this makes more robust for the reactive power demand by the this inverter circuit. So that then this H5 inverter have 98% efficiency. And but there is more loss because of the additional switch and cost also high. So that is what there are some problem. But then there are another inverter which is invented by Sunway, is one of the big PV company in Europe. This Sunway, how he designed, just he put this Herrick inverter. This is called Herrick inverter. You can see S1, S3, they are operated as a line frequency. Okay, switching frequency is 50 Hertz. And load two switches, S2 and S4, we use wide band gap device, such as the silicon carbide, gallium nitride device, okay, wide band gap device. So when you use that one, what is the advantage of that gallium based device or silicon carbide? Because the on-state drop is nearly zero. As drop is zero, you can operate at 1 megahertz also. It is easier for controlling like that. So like that, if you see here, this is our inverter. Upper two switch are based on the silicon, and lower two switch are the silicon carbide switches. So that is what you can see, that both the switch nearly the lossless, lower two switches. Upper two switches, you are operating at 50 Hertz. That's why low switching frequency, low switching loss. So efficiency also improve. So this is given how these are the control and how they operated in different modes. So yeah, so you can, by understanding this, you can easily understand how these different modes are operated. And you can see that the efficiency is around 97%. And two extra switches are required. See that the Sunway, they supplies this, the reported efficiency is around 95%. Okay. And then we have a large grid integration for megawatt range. So we go for multi-level. So I'll discuss more detail of this multi-level converter, especially neutral point clamped inverter, because this inverter is very powerful for connecting with the grid. So the main concept is that zero voltage can be achieved by clamping the output to the grounded middle point. And then you control this. You can see this is a neutral point clamp. You have two switches, 3 level. 3 level means you need 4 number of switches and 2 clamping, or you can say that clamped diode, D plus and D minus. And we have 2 switches on the top and 2 switches on the bottom. S1 and S3 are complementary. S2, S4 are complementary. So this way, you can easily control this one. Now, this is how the current and in the positive current and negative current flows. And this is the total technology, how it will be. But you see, they have a very low leakage current and also EMI. And that is what, these are the very reliable structure for the grid integrated system. Then the co-energy is also they develop based on the NPC inverter structure. And these inverters are very beautiful design. And you can see that you can achieve the neutral point clamping also by using this. So we can derive many kind of inverter structure, and this is how the operation takes place in different switching due to the switching at different switching modes. And the efficiency is higher than that one, and which is nearly 98%. So that is why this inverter was designed, and this is we implemented for some kind of solar plant, 10 kilowatt. Okay. So this is how our battery supported small microgrid system for IIT Patna. And this is what is our complete unit supplying one of the building. Okay, completely supplied by the solar energy. And we investigated for one panel. So what is the maximum power and what is the efficiency, and supply to different kind of loads. You can see we have taken three kind of load, and these three load have different kind of profile, and it is supporting to this. If you see the performance verification, you can see that this is the current waveform, which is actually not sinusoidal, and there are a lot of peaks also within, and that's why we need to verify this one. So before going that one, we will see a single phase, then we will go for a multi-level converter and large grid integration with the large power grid integration with the solar, or the solar interface with the grid. Okay. In this one, we will see some methodology. For example, a microgrid is a cluster of load and DGs energy storage. That is designed according to different rating. You have a different kind of microgrid. Okay, or you can have a AC, or you can have a DC, or you can hybrid AC DC. Like that, we can have a different kind of microgrid structure. And microgrid can operate in grid connected mode, standalone, and the transition between two modes. And you need to have output control, mainly voltage control, then power flow control. Okay. And third one is demand side management, economic dispatch, transition between modes of operation without interruption, especially from island mode to grid connected, or from grid connected mode to islanding mode. So that is how these microgrids are. Then there are classification actually. So with the microgrid, they have different classification: grid forming power converter, grid feeding power converter, and grid supporting power converter. So it is like your supporting system, and this is that your reactive power management is one of the most important things. So if you see here, there are two structures I have given. One basic control structure are the grid forming voltage source inverter. Okay, you can see this inverter, grid forming. Okay, this is connected to an isolated load and behave like a grid forming. Second one, grid feeding. You are feeding to the grid, okay, to your PCC. So in the grid feeding mode, you can see here, we measure mostly the VABC, and then we try to control this one. So the grid forming mode or feeding mode, you are controlling according to requirement of your active power and reactive power. Whereas the grid forming, you can see that you can just synchronize and try to maintain the voltage at the PCC. So when you see here, there are input side controller and grid side controller. So input, you have a DC-DC converter, what you do? MPPT tracking, input side protection, and boost up the voltage and DC link control. Where grid side control, grid synchronization, grid monitoring, active reactive power control, DC link control, islanding, and power quality. So like we see, sometimes there are marriage proposals. So the marriage proposal, what happened? There is a mediator to connect the girls' party and boys' party. And what they will do, they like carrier. This monitoring unit or that mediator will go to the boy side, glorify the girl side, and he will come to the girl side and then glorify the boy side. Exactly, input controller and grid side controller have the same features actually. Grid side want to become friendly with your grid side inverter want to feed the power by utility friendly way, and the input side controller, which is nothing but your DC-DC converter, he want to extract maximum from the grid side. And that is how they both are connected in this complete scenario. Now, what are the different techniques? If you take PWM-based technique, the PWM technique, they always give us a sluggish response, and you need to design a decoupled system. For example, in our DC motor, we have seen there is an armature winding and a field winding. And they both are perpendicular to each other. You change this armature winding, it will not affect on the performance of the field winding. You change the field winding, it will not affect on the performance of your armature winding. So that is how it is decoupled. Whereas in induction motor, you change A phase, it will affect on the B phase, it will affect on C phase because the machine is a highly coupled machine. This highly coupled machine, how to decouple is a big task. That is why in 1969, when Germany, one of the German scientists, he invented trans-vector control. How to make or how to analyze a induction motor exactly like a DC motor. That is the main which that is main purpose how the decoupling can be done. Now, this how we will do? There are many techniques. One of the technique is DQ analysis or converting from 3-phase to 2-phase system and then decoupling them. So there are current control technique. This current control technique is always, although it is independent. At the same time, it will give us completely decoupled system. So what is the advantage of current control? Current control, you see the current dynamic is very quick. And first, because the control is instantaneous, every sampling, the position of the current changes. And this current technique, especially, they are instantaneous, this current waveform, they control instantaneously. For example, you give a slap to a boy, he also give back a slap. That is instantaneous. Or if there is some senior people, like in our childhood, our parents will give a slap, that time we will think that, oh, when I will become young, that time I'll give. So that feeling during the childhood automatic come. That means that is called the sluggish response. Then you will become young, then you will give that. Whereas this one is very quick. So that is called the current control. And the current control technique is always nonlinear. Like a switch is a nonlinear system, and current control technique nonlinear. So they both are the same plane. For example, if you and your roommate both are you are a pure vegetarian. If your roommate also became pure vegetarian, you will always enjoy his company. If you are, or you want to go to movie, and like I used to stay in Parvatipuram, and I had my roommate, and that roommate is always interested for watching Telugu movie. But I am from Odisha. I do not know Telugu, but I like to watch. So he will always go. That movie is Annaya. There was one movie. So he visited at least 10 times. Every day he will call me. But I became very disturbed because yesterday we have seen 2-3 times I have seen. Like that, you need the current control and nonlinear system. They both are synonymous. That is why the current control can have highly accurate. And there is a peak current protection, overload rejection, extremely good dynamic response. Okay, extremely good dynamic means you suddenly want to change. There is no sluggish effect on the system. And then it will reduce the THD, and also you can maintain the DC link voltage very nicely. And another one is it is independent of load parameter. For example, you are going to college and there is some problem in your family. Suddenly your mind or your feeling goes distorted. So, but those who are the sthitaprajnas or those who are self-realized people, whatever things happen, they never worried. They are very much interested what to do. So that is how this current controller became very, very important. So we will discuss more in this current control. We will go. You can papers are published in IEEE transactions also, IET also. Lot of papers are there, and the simple current control technique. Okay. Just now we sent to one IEEE in application. So that may be coming in between 1 or 2 months. So these are the very important things. So the linear controller have good steady state performance, less harmonic content with fixed switching frequency, but its performance can be greatly affected by change in the parameter nonlinear load. That is why they are a little bit relatively complex algorithm and difficult to tune and analyze. So you see here, a simple PV system with a DC-DC converter connected to the common DC link and inverted through filter connected to this AC system. Okay, this is the complete control. So the average modeling of the inverter, if you see a inverter with L filter, okay, only grid control or the grid control inverter, you can see here, there is a series inductor which is connected to this, you have a VDC and V output. You can write a simple equation, the KVL equation. That is what this is the beauty of this one, this system. Now, this you can have one of this capacitor filter, okay, but you have a LC filter connected in this grid connected system. You can write down this mathematical equation where U is our switching function. What are the switching function? We will discuss. So when you have a LCL filter, we can model U. You can see here, I have given here U is +1 when S1, S2 is on, and -1 when S3, S4 is on. Okay, and you can write down the equation. And the simple KVL equation is Ri Li, then minus Vc plus Vdc into U. So on this one, you can write down the state space equation, and U can be defined as the switching function when S1, S2 is on +1, S3, S4 on -1. So this system, you can write down the transfer function of this one. Okay, this is our transfer function. And this transfer function is written in the state space equation. And this is our controller. You see here, this is our S1, S2, S3, S4. And this is a solar and connected to solar filter, to inverter, and then connected to the grid. And according to I reference, we trigger by using, or the gate driver, we use this hysteresis current control. So what do you mean by nonlinear system? Most important thing, linear system, everybody knows, you have a bounded input, you have bounded output. Or if it follows simple thing, we say that if the it follows the superposition and reciprocity theorem, or then it is your linear system. Reciprocity, reciprocal theorem. Okay, so that too follows. It is a linear system. What do nonlinear system? Nonlinear system means the system which doesn't have bounded input and bounded output. That means, for example, you come from your office, while coming to your house, suddenly somebody called you and told you, "Arey, you got a lottery of 10 lakh rupees. Please come and collect." So what is your mind? You will think, even you are distressed, suddenly that person become very happy. Oh, I got this one. For example, one of our relative, he purchased a fridge, 1.6 lakh rupees fridge. And then they got a lottery of 40,000. Still they they got the lottery, they put in the Facebook, the status, and the WhatsApp message, everywhere came. Why they are happy? They don't know that they have already spent 1.6 lakh rupees. That is why they gave them. So still, that is some kind of this thing. So that is what the nonlinear system is like, exactly like that. That it changes with respect to the environment and changes with respect to different dynamic. It changes with respect to the initial or the final condition of the system. That is why the nonlinear system are very difficult to analyze. So what we do? Generally, we do linearization, all the thing, and then we design a controller, we run our converter. But a nonlinear system, you want to analyze like a linear system, that means you need a lot of approximation. So because of that lot of approximation in our system, and that will give us more controlling capability into that system. So that is why the hysteresis current control is one of the nonlinear element in the control structure. You have all this PI controller is your linear controller, but in that controller you have a nonlinear element. That means your linearized controller, you are operating in the nonlinear mode. And that is why in this one, we will see 4 kind of hysteresis current controller, which is very important. First is single band hysteresis control. What do you mean by hysteresis? Like in our transformer, we have a different, we know that steel has a different VH core. If the core is having wide and more loss, if it is very thin, that is loss, very low loss. So that way, this exchange of this one is the most important thing, is that there are different kind of the hysteresis band. Hysteresis means like you have a BH core, the operation exactly like a hysteresis band. Why we do generally hysteresis band? You can use the signum function also. It can give +1, -1. If the error is greater than 0, it will give +1. If the error less than 0, it will give -1. So why we use hysteresis current control? Hysteresis actually decreases the switching frequency. For example, you have IGBTs, they are 20 kilohertz maximum switching frequency. But with the error go from the origin, that operated very high switching frequency, which will damage your IGBT, insulated gate bipolar transistor, as a switch we use. So double band hysteresis current control, and then we will see modified double band hysteresis current control and adaptive hysteresis current control. We will see here. So the current control of the inverter, you see, we have S1, S2 is on, and this is equation number 1, you can write down. And when S2, S3 on, you can write down the equation in the number 2. Now, how you control? You see, this is the hysteresis current control. You can say this one. When it is greater than plus HB, HB or minus HB. If you see, 2 HB is your bandwidth of this hysteresis controller. So it varies as when S1, S2 on, then you connect to the positive rail, and S1, S2 on, you connect plus VDC. When S3, S4 on, you connect to minus VDC. So the same thing is written here. When the T on, S1, S2 is on, which connect to plus VDC, and during T off time, we connect to minus VDC, which is minus of VDC. You can see the switching signal is exactly like that. So as your hysteresis band, you increase or decrease, it affects on the output voltage performance. And if we see from those equations, you can find out what is the on time and what is off time. You can see that they are function of inductor, they are function of grid voltage, they are function of DC link voltage, and function of hysteresis band. Then from there you can find out what is the switching, what is the relationship between the switching frequency. Okay. Now you can see that this switching frequency is function of VDC, VG, and L and HB. Okay. So from there, you can find out what is the maximum switching frequency, and the maximum switching frequency is written in this one. So once you know the maximum switching frequency, now you can choose your device rating, because this is the maximum frequency. You choose the device rating, then you use that device here. Now you see here, I have put here another technique is the double hysteresis band. Double hysteresis band, how it is, you have two bands. So one is, you can see here in this triangular, this positive band control and then negative band control. So when you in the use it, you can see that for plus HB, you have a positive VDC, and for T off, it is 0. That means what kind of this output you get? It is unipolar output or unipolar PWM technique. Okay. So this hysteresis current controller gives you the unipolar PWM type of waveform, and this can be easily, you can control and monitor for your output frequency. So here also, we found out this is our frequency. But if you see, these are the two techniques that this is your double band hysteresis technique, and then we are using this one for switching this one. For example, this red color, you can see here, how we turn on, you turn on in this way, and then you come back like this, and this is your larger band. And then there is a smaller band, okay? And these two are controlled. And then for 0 to minus SB, okay, you can control the diagonal element, okay? This is which is shown in this circuit. So this double band circuit, what you require, you need to get 0, 1, 1, 1, 0, 1, 0, 1, 1. This pattern you need. So when you need this type of pattern, so what you need to do, you can design a simple, draw a K-map, and then you design a simple, by using JK flip-flop, we can design this controlling circuit or the triggering logic gate circuit. Now you can see that whatever the frequency, whatever the time we got, now you can verify this one with the simulation system. Now you have seen that this frequency is dependent on this one. For this parameter, you can find what is your frequency and verify with your simulation result what you have. Now here you see, then we have an adaptive hysteresis band. Adaptive means, for example, long back I visited to Badrinath. So first day, and I supposed to visit to one place called Mana. And while going, I had no socks, I have no winter cloth. So it was very cold actually. And it was July, so it was very cold there. So as first day, it was very cold. And next day, because I don't have anything, nor there is any shops are there also. Few shops were there, but which was not, you will not get better thing. So this, when I want to purchase and use it, next day, I became habituated. After 3 days, I have seen that we don't require things because you adjusted that. Exactly, the adaptive hysteresis control based on output dynamic, based on the parameter change, all these things are dynamically controlled. That is called adaptive hysteresis. You adapt to the hysteresis band according to your load requirement, and that is why in the equation number 24, you can see what is your adaptive band. It depends on this complete system. And you can find out what is the switching frequency also. They also depend on that one, actually. So that means you change your hysteresis band or change your switching pattern according to load requirement, so that you will get maximum, maximum output. So then we did with the simulation result in MATLAB environment, and we have 400 volt DC link voltage and inductance of 10 millihenry and load resistance of 50 ohm. And reference current is 10 ampere. So like that, we designed this one. You can see here, this is the inverter output, okay? It is nothing but a square wave output. And you can see here, the switching frequency. Switching frequency average, you will see that it is actually between 20 kilohertz, okay? So maximum switching frequency 20 kilo. Now you see the current at time at this point 0.85. The reference current changes. Okay, it was flowing actually around 10 ampere peak to peak. So this current suddenly changed at this 0.85, and you can see that current is perfectly tracking the reference current. And at the point of 0.205, again you step change the current, it is perfectly tracking this. And this is how the complete unit is perfectly designed. The closed loop control is working very nice. Now, double hysteresis band, you can see here, this is the output voltage. It is unipolar, and we have already seen. Unipolar means plus 0, or minus VDC 0, minus VDC 0, minus. And this is reflected in this figure number 1. You can see here in the up top one. And then this is your error, tracking error. Okay. Now, below that, the switching pulse of S1, S4. Okay. And you can see here the current, load current and reference current, both are tracking each other according to the dynamic change of this current. Now, this is our switching frequency, okay? You will see the switching frequency is limited to 10 kilohertz, and the pattern is exactly like this due to the double hysteresis band. So double hysteresis band will give you two peaks, you can see here. And then we have a switching path like this. Then we have again this changed this one, the different switching frequencies, and this you can see here the same kind of waveforms. Okay, but here in the error you can see because of the PWM kind of they change the hysteresis band, you can see that the current ripple decreases. Okay, very small. Now, modified double band hysteresis control, which we have shown, I already discussed it before. You can see that they also gives tracking, okay, according to their the current, there's a sudden current decrease, so it is also tracking the same. So this way, we have implemented very nicely all these three techniques. So you can see here, in the current for single band, you can see that your switching frequency is very high. This third one, in the top third one, you can see that switching frequency is very high. And little go, you have the switching frequency is reduced, okay? And you go above one current for modified double band, you can see that the current is the switching ripple is very small as compared to both these. That is what it is the modified double hysteresis band have less current ripple. Then you see here below also the comparison of this. So you can see from this current, you can see this voltage. You can see there are a lot of this switching take action. So that means switching frequency is very high here, and the double is a little lower than this below one. And top one, you can see that the switching frequency is reduced drastically in the modified. That means switching frequency reduces means what you gain high efficiency, low loss, and the switching ripples are also less. So similarly, you can see in the below also this is the error signal. Okay, you can see that there. Now, this is the result from the adaptive hysteresis band. So by seeing the error signal, you can understand that it is adapting in every cycle. Okay, every half cycle, it is adapted. You can see that it is very nicely controlled. Hysteresis band, and upper one is our current, and lower one you can see that if there is a change in the reference current, automatically actual current tracks to that one, or it follows the same path. And that is means the closed loop control is perfectly working. And now we implemented this complete unit in a hardware setup. And this hardware, we use only 100 volt DC. And then we have 5 ampere current reference. And we validated the same thing. You can see here, the first one is the current. Then second one is your voltage, and third one is your tracking current. Okay, error signal, tracking error. So this you can see that all these three figures are perfectly designed and implemented in the laboratory. And then the hardware result of you can see that the reference current and the actual current. And this reference and the actual current are the most important thing. As you reduce the hysteresis band, the current ripple or the current band will also reduce. But you cannot reduce so much also, because if you reduce so much, it will cross the boundary, which is called hysteresis tolerant band. Okay. So this way, we implemented the double band hysteresis current control, and you can see that the voltage is our exactly the like a unipolar signal, and the current signal also you can see that this this current tracking is also improved, okay, by using double hysteresis band. And you can see that in the below the reference current and the actual current. Red one is our actual current and the green one is our reference current. Now, this is, you change the different switching frequency, you can change this one. So these are the exactly different and the double band hysteresis current. And this is implemented also in the hardware. And you can see that here there is a change in this the reference current. So this also follow that reference current. And below in the figure number 29, you can see that exactly the simulation result what we did at 0.85, suddenly there is a reference current change, and at 0.25 second also it is suddenly changed. You can see at this moment the complete this tracking performance is perfect and it is very fast. Okay, so that is how this is implemented. And now this is the hardware result is modified. You can see that switching frequency are less, ripple are less, and that is how the switching the losses are less, and then you can actually operate within the given switching frequency. Now this is another hardware result where you change the reference current and accordingly this is tracking and it is perfectly done. In this one, what we did different hysteresis current control technique. We understand what is the hysteresis current control and what is the modified double band and double band, and as a simple agent. Then we used this one for controlling a closed loop inverter system feeding to a grid. So there are a few references and you can see this one. If you have any doubt or comment, we will discuss. Then we will go to another part.
Yes, participants, if you have any queries related to the topic discussed, sir, right now, you can raise your queries. You can unmute your mic and raise your queries. Yes, participants, you can unmute your mic and raise your queries related to the topic sir has discussed. Yes, sir. Yes, sir. I think we don't have any doubts, sir.
Okay.
Yes.
So now we will continue this. Okay. So if you have any doubt, now we will go a little advanced current control technique. The modeling of utility friendly 3-level. Okay, we have seen 2-level converter. Now we control that one. Now we'll go a little bit higher level as a 3-level. Okay, so this is a 3-level converter. You can see I have already shown you here. The 3-level is this one. You see, you have an input inductor and 3-level inverter. Okay, there are 3 and 12 number of switches, and there is a 2 DC links are connected, DC capacitor in series, and then you have a load or a gray or your DC link. Okay. So there are different kind. One is fixed hysteresis current control. And this fixed hysteresis current control, already we discussed what is the purpose. This is a block diagram. You want this IA to be controlled. And you want to control this IA, IB and IC. So you give the reference. And this will have your actual current IA, IB, IC. Then we have this hysteresis band, and then you have a decoder and lockout circuit, and then you can trigger you apply the gate pulse to this 3-level inverter. And this 4, 4, 4 I have given, each component it says 4 switching signal feeding to this inverter circuit. And then we have these 2 capacitors, C1 and C2, and connected to the load. So sometimes this is called the open loop system. Okay. This open loop system, you have a reference current and actual current feeding here. Now I want to have a closed loop control because I want to maintain this DC link voltage constant. Or when you are feeding to the grid, we should have this, the PLL here in this. And then this is the complete control unit. That first is your outer loop, which is a voltage control loop. And there is an inner loop control, which is a current control. The IA star is actually it is measured or is compared with the actual IA. IB star is compared to IB, and IC star compared to IC. So if you write down the state space equation, it is exactly like this. Okay, you have a state space equation, A, B, C, D parameters are given here. Now, if you simulate this one, you can see that DC link voltage is 300 volt, and you can see VAB, it is nothing but you have 5 level because each phase you get 3 level. So line to line voltage you will get 5 level. So you can see that here it is like a 5 level output. Then your current and voltage, they both are unity power factor. That means this converter feed to the grid or absorb from the grid, they are always maintained at a unity power factor. And the VDC1 and VDC2, you can see they both are balanced and constant here. Now this inverting mode. So this inverting mode of operation, you can see that when the DC link or reference voltage in the DC increases more than that one, suddenly at that moment, your capacitor voltage or the current in the injected current are unity power factor, but in the opposite phase. So that means the converter operates at power factor 1 and it operates at power factor -1 when it takes power, and when it supplies the power, it is +1. When it takes the power, it is -1. Okay, that way we can see that it is. And there is a sudden load change also. This sudden load change, you can see that due to this load change, you can see it affect on the performance of this current and voltage. And you can see here, as soon as you have a load change, you can see that switching frequency of the inverter output is reduced. Okay. Now we will go through this complete unit with the switching characterization, which is a very important thing. And in this scheme, we will use three kind of switching scheme. One is our 3-level switching. Second one is forced switching using single carrier injection. And third one is forced switching using single carrier injection with reverse polarity, which is a very important technique. First thing, why you need forced switching? For example, somebody, you called him, please come to my office. So he has not come. So what you do, you go with to him and pull him to your office. And this is called the force. Okay. And similarly, sometimes there is a wind and there are boats in the sea. And the boatman wanted to go to inside the sea. So if the wind will blow from the land to sea, automatically the boatman will get the wind which is in his own direction. So he became happy. So similarly, the force switching technique. So what we do, because switch means it always creates the dynamic. So you create an opposite dynamic which will cancel both the dynamic. Always both the system will behave like a steady state system. That is the main thing of this force switching technique. And whether it is along with that or it is in the opposite direction, that is different. You see here, this is the 3-level switching. 3-level means in positive half cycle, you can see that there is a positive square, and in negative half cycle, there is negative square, and then we have a 0. That means we have a 1 level in the positive, and from between the positive minus alpha to alpha, that is 0, then minus alpha to minus alpha plus h, okay, the negative. That is how the 3-level switching action takes place, and this is our switching logic. Now, the same switching frequency is added with a carrier frequency. For example, this carrier is small, which is equal to the ripple current of the current. So that carrier is injected to the ripple content. That means this carrier can cancel out the many unwanted thing in the tracking error, and then that will pass through this switching 3-level will give you. You can see here the frequency became unipolar. It is unipolar switching. At the same time, they have a constant switching frequency which carry. Okay. And then we have seen there are another technique which is single carrier injection with reverse polarity. So you have a tracking error. Now you inject the same thing with one is in the same polarity, another one in opposite polarity. So when you are feeding to this hysteresis controller, you can see during the middle point, there are a high switching frequency, and in the both the end, it is a low switching frequency. Whereas in conventional method, we have seen initially it is a high switching frequency, where after the low switching, but here it is just opposite to that one. Now this is our control structure that we have the VDC link, like we have seen, like then we have a current controller and timer, then sin theta, then actual current is compared and passed through the nonlinear hysteresis controller. Now, how to design this switching function? which is another important aspect. Like we will use here as a frequency domain analysis. What do you mean by frequency domain? There are two types of domain. One is your time domain. Another one is frequency domain. In time domain, everything became very complex. You need multiplication, you need division, everything. Where when you convert to frequency domain, the same multiplication division became an addition and subtraction. And that is why the frequency domain analysis is very, this frequency domain technique is very well received by the scientists as well as the industrial applications. That is what the Bode plot is. Today we also use Bode plot as for understanding how to analyze the stability of the system. Easy became, okay, because it is algebraic equation actually. And that is why this is one of the important techniques. But here we will use the frequency domain analysis, and we use describing function. Describing function means like we have a transfer function, and the transfer function is nothing but nonlinear transfer function is called describing function. And describing function is a big topic, and we cannot discuss here. You just understand that describing function is nothing like in a linear system, we find transfer function. For a nonlinear system, we find the describing function. The same thing. And then Simpkinson's locus, which is very important. So what we will do to find maximum frequency prediction. Second one, stability of the system. We want to discuss this one. Now, if you put this transfer function of this plant is something like this, second order system. Now, this frequency domain analysis, we will write down the describing function of the hysteresis band, which is depend on X and H. H is your hysteresis band and X is your tracking error. So it can be written as in this way, where M is +1, 0, -1, H is your hysteresis band. So by using Simpkinson's method, that this hysteresis band H can be found out, which is equal to this one. So what you are getting, the hysteresis band, it depends on the gain of the plant and the inductor and the resistance value. So what we do, we did the magnitude and the phase plot. You can see here, this is the magnitude. For different frequency, F is equal to 3.8 kilohertz to 15 kilohertz. We started analyzing this complete unit. And if you see here, the transfer of the magnitude plot and imaginary this magnitude plot if you draw here, okay, by putting this one, then you can see that there are a lot of interactions. Okay, there is this is -1 by Kn, which is nothing but this is the line which is constant for different value of this H. And they are interacting, or WP3, WP, W2, W1, these are the crossing. At that time, you have to find out what is the magnitude of frequency, then automatically we can design the hysteresis band. So this is also very, very important aspect. First thing is stabilization. So how to stabilize the system? First thing is to stabilize means your base must be perfect. And second thing, and the transient response, they should continuously control and it gives continuous change. And the switching frequency as same as the injected frequency. And ripple will not be seen in the output circuit. Then we have the stabilization. You can see you impose or superimpose this 3-level switching plus this carrier one. It is exactly look like this. And if you see, this is our deriving function, and it is within 0.481 to 1. So at that time we try to understand the carrier signal. So what we did, you can see that at which point there are a minimum current ripple. You can see at 0.5 amplitude carrier, you get 0.2 current band, and which is a normal operation at that time. Above that, you get overmodulation, and somewhere you get the higher ripple. So that is why we choose the carrier amplitude as 0.5. And then we have a complete system. And then this complete system is analyzed VDC star with respect to VDC, voltage controller, and then limiter. Then we have a current controller, nonlinear hysteresis current controller, then the plant, and the system dynamic. And you can find out what is the transfer function of the complete system. This is the complete system transfer. And then this is our stability study. You can see that all the poles and zeros are the poles are on the left hand of the S-plane, so that the system ensures stability. And if you see the harmonic spectrum here, you will see that there are different kind of the switching technique, this 3-level technique, this 3-level switching technique. Actually, he got the switching technique, we got this lowest switching loss. Okay. And these are the harmonic analysis. And you see here, total converter loss is very low in the 3-level switching, and fractional of output power and efficiency, you can see that it is the maximum, okay, which is nearly more than 96% of the efficiency, okay. Now this complete unit is implemented with a 3-level converter, and this 3-level converter is designed, and after this design, this hardware result were obtained. You can see here the left hand side, it shows the simulation result, and right hand side shows the experimental result. In the simulation result, you can see the green one is our tracking error, and these are the switching signal. And exactly in the hardware also, same tracking error and the same type of the switching signal obtained. That means both hardware and simulation, they both are perfectly matching each other. Then the DC link capacitor also exactly. You can see the simulation, and here is the hardware. In the 3-level, you can see that both current and voltage, they both are unity power factor 1. You can see here also power factor 1. And VDC1 and VDC2, you can see here, they both are same as this simulation result. And you see here, this is your current reference, okay, the phase current, and you can see this actual current by in this current tracking. So ripple in the different phase current, you can see where different hysteresis band, you can see that at H is 1.5 the minimum ripple content. So that is what minimum switching frequencies operate. So that means you can monitor under all hysteresis band, your converter is operated within the limited range. So that is always maintained stable. Now this is forced switching in carrier injection. You can see that this is the tracking error and this is experimental tracking error. And this is our switching signal simulation and the switching signal in the experimental. So this also you can see that both are sinusoidal and in phase, and this is also sinusoidal in phase also, and this link control DC1 and DC2. Okay. Now this forced switching technique is using single carrier modulation. You can see that switching frequency is nearly 3 kilohertz. And that means the forced switching technique, you can see that ripple content is more as your frequency reduces. And this is the simulation experimental region. And it is a total harmonic distortion. You can see here 3.2%, 3.4%, and 5.4%. This is practical harmonic spectrum, okay? So this is how the complicated unit can be designed very beautifully. And the conclusion is that the hysteresis band switching technique are very easy and we can control by using the nonlinear way. And second thing, Simpson's method with describing function, it gives a more accurate result for switching carrier implementation. Experimental results are presented. So we stop here. If you have any questions or comment, and we can discuss.
Yes, thank you, sir. Participants, if you have any queries related to the current control device or current control converter, which sir topic has discussed right now, you can raise your queries.
Queries or comment also, no problem. If they want some improvement also, we can.
Okay, the
Yes,
session is
participant.
complete, right?
Yes, sir. Session completed. Yes,
There are
participant.
No, actually, if there is no questions, then we can discuss the last part, that real power MPPT technique actually. So if there are no questions, we can continue with that session. Little 15 minutes, I will try to finish it.
Yes, sir. You can continue, sir.
I can continue?
Yes, sir.
Okay. All right. So today, this is our work on real power maximum MPPT during partial shading, which is generally we don't consider during partial shading, but I will discuss very quickly this part actually. This is the VI characteristics of a solar cell. When there is a dark, you can see that the solar cell behave like a sink. not the source. That is why there is another requirement of the solar MPPT tracker that during partial shading condition, this solar cell should not absorb the real power. And that is why in the night time, you will find that there is a series connected diode to this solar plants. Okay. So these are the PV curve. If you can see VI curve, which changes with respect to the irradiation, sunlight. And today we will discuss the partial shading condition. So during partial shading, the shadow due to building, trees, cloud, etc. One part of the panel is shadow, other part having full sun. So that means the local one portion of your solar plant is the observer, other plant is giver. So in that condition, how you can find out the maximum power point tracker? So which is very important to design. There are many incremental Potter observe method. There are many MPPT technique we are not going to discuss. But today we will discuss only the partial shading condition, PSC. Under this partial condition, you will get local maximum, so many minima and so many maxima. This means that some panel will perform below their MPP, resulting in the loss of energy. Power loss can be very high. In some case, up to 70% also. So if you see here, just I have shown you, the conventional method, what we do, if it is perfectly like this, that MPPT, it will work very nice. If due to the partial shading, your A point will come to B and C, it divide like this. So it will be so many maxima. One is C is a maxima, and B is also a maxima, local maxima between this range. So what will, if the A, suddenly there is a partial shading, it will come to B point, and B point is already at a maximum because it will see this side, there is a dip and that side also a dip. So it will try to fix at this point as a maximum, but the actual maxima is where the C point is the actual maxima. So, but because it shifted to B point, it will not go to C point because it looks here locally that this is the maxima. So why it will go to C? Even he don't know that this is the maximum, the MPPT point, the real MPPT. That's why when there is a partial shading condition, the most important thing, the local minima became the maxima. The real maxima, we cannot reach there. That is why we need to understand the solar plant during especially in the partial condition. So the solar cells can be, you can model like this, actually. We are not going detail. This is already there. Then you have a number of solar cells, like in Port Blair Airport Station, we put nearly 1 megawatt solar plant. So you need to design. NP is the number of parallel path, NS is the number of series panel. So when you have a parallel and series, you can write down the current equation for the solar module is like that, okay, NS, NP. Then you have current and other output current equation is like this. And then model of the PV is carried out, and this is shown as a design IA and then ISC how many. So accordingly, this is the output current equation. We put all the variables. So for example, now you see each module you try to draw. So if you see here, 3 modules are there. Here 3 modules. In these 3 modules, you will get IV curve like this, 1, 2, 3 module. And for this, you have 1, 2, 3, 3 module. So overall, if you see VA is nothing but this red line, which is called the actual condition. And similarly, the red line is your PV. Now, by by shadow, you have a shadow, okay, due to a tree. One of the panel is covered. When as soon as it covered, you can see that your PV curve became actually like this. Actually, it was not only one maxima, you have multiple maxima. You see, the local maxima or MPP is here in the C, you can see, but the actual real MPP is here. And then you have n number of cells, okay? When you have a setting, then you get this equation. Now you see here, when you are changing to coming to B point, this point it will see as a local, it will reach to the C point. So what we will do, first thing is that you can see the PV curve. First, at the A point, it will come to B. And from B point, what we will do, it will shift to C, not to other point. What we will do, we have a power and voltage curve, and that will shift to your C point. And from C point, it can travel to this one, because C point is higher than the B point. So what are the algorithm here is obtain evidence that PSC has occurred using the variation of the input voltage, and then move the operating according to predefined linear function, and then track the MPPT tracking. Okay, this is the flowchart diagram. And if you are interested, there is a paper which we have written long back, and on the MPPT partial setting, then completely it is. So now in the proposed MPPT, how it comes like this. The come is that here the A point will come to B, B point to C, C to D point. And this we can get in the low voltage level. This is the method of getting the real MPPT tracking. For example, sometime at a high voltage level, you can see the A point was there. Suddenly there is a partial shading that will come to B point, and B point will go to C point, and from C it will try to track and come back to D point. And when you have a medium voltage, you can see that A point will come to B point to C point, C to D point. So in this way, the tracking, you can track the real maximum power. Okay, like that, you see here, this is conventional, the source charging. So you can see that there are a lot of chattering, and it comes to track to the maximum power. So similarly, in this one also, you can see the shaded portion. You can see they always try to. You can see that there are the chattering and reaches to this maximum power point. Okay, so this is how you will see here. During partial setting, it comes to this point, and from here it comes to another point, then go to this low line, and then it tracks to your maximum power. Now, for different irradiance, this is shown the performance of the irradiance. And then this system is implemented. Okay. So this what we have a PV panel and a boost converter, then inverter connecting to the grid. And we have a MPPT tracker and a boost converter application. So you see that we have taken that the series 20 number, parallel 2 number, and this is the complete specification of the solar. Now you see here, this is our the without any partial shading. This is our MPPT system. Okay, this is occurring and MPPT was, and below is your power output. Okay. Now, at this point, you see this is the experimental result. Okay, and then this PCS, when there is a, now it is our current is feeding to the grid, and this is our output, and the operating point is here, IP. Now suddenly there is a partial shading, so you can see that this curve, and the output power is drastically decreased. You can see here power output, both voltage and current are decreased, so also the power decrease. Now, this is our experimental result. You can see the output power decreased. And the grid voltage also remains same, but the current decreased. And then what, so you can see that this is, when we use this method of our proposed method, suddenly it is tracking to the real MPPT point. That means you can see that as soon after some time, the power increases. Okay, so you can see that 1.6 at second, the power decreased due to the partial shading, and because of our real MPPT tracking, the power increased. So you can see here also, the power was decreased. Again, because of the real MPPT tracking, the power output is, again, it is increased. So this way, we can conclude that the real MPPT tracking will be designed, and the experimental result are very beautifully explained, the simulation result. And these are the few references. And if you have any questions or comments, we will discuss.
Yes, participants, if you have any queries, you can raise your doubts. Jay Krishna, sir.
Okay, sir.
Yes, sir.
Yes, sir.
Sir, thank you very much for your session, sir. It is very nice. And thank you very much for accepting our request, sir, Ranjan, sir. Now I request Mr. K. Gopinath, Assistant Professor of EEE Department, to propose vote of thanks for today's session.
Yes, thank you, sir. Good afternoon once again to one and all. Honorable Secretary, sir, Principal Madam, Convener, Co-Convener, and fellow faculty members, and all the participants. It's my immense pleasure to give vote of thanks to today's research person,
Yes,
Dr. Ranjan Kumar Behera, sir. Yes, sir. It's my immense pleasure to give vote of thanks to Dr. Ranjan Kumar Behera, sir. 1 second, sir. Let me mute all the participants. Yes, I am on behalf of St. Peter's Engineering College and organizing team of this STTP propose vote of thanks to Dr. Ranjan Kumara sir. In this lecture, Dr. Ranjan Kumara sir has discussed different types of inverters, current control inverters, and few of the advanced current just normal inverters like H5 inverter, HERIC inverters, and then sir has discussed and classified different types of microgrid power inverters, and then third moved on to the different classifications of hysteresis current controlled inverter, like a single band hysteresis current control inverter, double band hysteresis current controlled inverter, and few more different types. And sir has discussed with a double band hysteresis current control inverter with a detailed simulation which sir has done in his research field. And then said moved on to the few of the advanced nonlinear converters to integrate power PV system with a power grid. And sir has discussed different parameters that are need to be considered for effective integration of power PV system to a grid. Thank you, sir. Thank you for your wonderful lecture on advanced power converters for solar energies. And once again, thank you, sir. In spite of your busy schedule, you accepted our request to give a wonderful presentation in this session. Thank you, sir.
Thank you
Sir,
very much,
Ranjan
sir.
Kumar,
Ranjan Kumar, sir.
sir, unmute your mic.
Now is it audible, sir?
Yes, sir. Audible, sir.
Yes, sir. Now it is audible.
Okay. Okay. Thank you so much, sir.
Thank you very much, sir.
If you have any comment or question, they can write my email also. I have given my email address. In PPT, I'll send you, sir, quickly. Okay. Thank you so much.
Okay, thank you very much, sir.